In this paper, we consider effective time step restrictions for explicit material point method simulations. The material point method is a numerical method for simulating complex materials, introduced into graphics for simulating snow, but it's also quite effective for sand, fluids, solids, and other complicated materials. Time step sizes must be chosen carefully for explicit material point methods to prevent them from exploding, as you can see in this simulation. In particular, choosing the time step size based on the current velocity and grid cell size is not sufficient to maintain stability. In practice, fixed time step sizes are usually used for a material point method, and they are chosen by trial and error. In this paper, we consider a set of 5 time step restrictions, which we use to stabilize our sims. The first of these 3 are heuristics based on restricting the amount by which the particle state can change. The 4th one is the classical CFL restriction for stability. And the 5th one is a novel instability that we discovered in simulations when particles become isolated. Under most circumstances, the sound speed is a very good predictor for what a stable time step size should be. And deviating from this by even several percent can often be capable of destabilizing the simulation and causing it to explode, as you can see here. In Feng et al. 2018, they also used a sound speed approximation to choose their time step sizes. In their case, they used an approximation from the mechanical engineering literature, which approximates the sound speed based on an estimate at the rest configuration. Here we compare this approximation to the exact sound speeds for an isotropic constitutive model. We see that the approximation both underestimates and overestimates the exact sound speed. We note that the approximation is exact at the rest configuration, where the approximation is valid, but otherwise it can deviate quite significantly from the real sound speed. One of our main contributions is an analytic derivation of the exact sound speed for general isotropic hyperelastic constitutive models, which to our best of our knowledge has never been published anywhere. But even fixing the time step sizes for sound speed is not sufficient to necessarily stabilize a simulation, as can be seen here, where particles very quickly become unstable once they become isolated. Tracking down this instability leads us to another time step restriction, which, when we impose it here, is sufficient to stabilize the simulation. We note that the only means that we are using to stabilize these simulations is judicious choice of our time step sizes. This also suffices to stabilize all of our other simulations as well.